Hello everyone, and today I'm going to bring you a beginner level overclocking guide for RAM. Specifically as an example, I will be using DDR4 today, but this will also apply to older things like DDR3 and newer things like DDR5. So the first thing we're going to talk about is just general description of how memory performance works and what actually gives you high performance. The second thing we'll be talking about is memory ICs and why they are important. The third thing is how we identify memory ICs. And then the fourth thing is just some more general advice to keep in mind, some smaller details like PCB differences and just closing thoughts. So, first thing, how does RAM really work? RAM is a bit unique because most other things like CPUs and graphics cards, higher clock is just always better. Now RAM, that also works. Higher clock means more theoretical bandwidth and is therefore better. But the thing with RAM is, it doesn't just have adjustable frequency, it also has adjustable timings. Now you can see this in pretty much all XMPs. For example, it says 3000, 15, 17, 17, 35. Those are the listed primary timings that this XMP is rated for. This one says only the cache latency, which is CL19. This one also CL17. So there's timings for RAM. And the way how timings work is each timing has an associated action that the RAM can perform. Well, more the memory controller can perform using the RAM, but for simplicity's sake, let's say the RAM performs the action. And that action is performed in clock cycles, which is a delay that the RAM needs to perform the action. So that already implies if you have a higher frequency, a certain action will need a higher timing, because if you have more clock cycles per second, you will need more clock cycles to get the same amount of delay in seconds you need to finish that action. So, for example, if you have 3000 megahertz CL15, it will be the exact same latency as 3200 CL16 to perform the cache latency action. It's what the RAM timings actually do is kind of complicated, and I'm not going into that. If you want to learn what exactly they do, Buildzoid recently made a series of videos about what they actually do, what actually happens inside the rows and columns of the memory chip, how they get accessed, how they get read, how the read burst works, how they get pre-charged and all that stuff. But basically, just remember each timing has an action associated with it, and the memory timing measures the time that this action takes to complete in clock cycles. And clock cycles are relative to, of course, your clock speed. So that's basically how it works. So having a high frequency is good for your theoretical bandwidth, and also because it ties in with other things like your memory controller clock. But having low timings means that it will perform the actions faster. So basically, high frequency, low timings is best, and low frequency, high timings is worst. In terms of priority, it's a bit complicated, because usually you would just go as high of a frequency as possible and then just take the lowest timings that work at that frequency. But there's a problem, and that problem is called Ryzen. Because Ryzen has the Infinity Fabric, also short FCLK. And usually the FCLK can't clock higher than 1866 or 1900 megahertz. And if you go higher than 2 times your FCLK in RAM, you tend to have a performance penalty, because your RAM might be ready to receive or send data, but your FCLK is currently occupied with doing something else and has to wait a little bit before it's ready to start a new clock cycle and actually do something with the RAM. So most people on Ryzen prefer to remain synced, which means that your RAM clock is 2 times your FCLK. That's why most people like to run 3600 to 3800 megahertz RAM on Ryzen, because that means your FCLK will be the fastest and it will be synced to your RAM clock. And the reason why it's 2 times is because DDR stands for double data rate, which means that your actual DRAM clock is actually half of what you have. So 3600 is actually, good question, 1800. And 3800 will be 1900, and then 3200 is 1600, and so on. So, yeah. theoretically saying megahertz is also wrong. You should be saying DDR4 3600, because 3600 megahertz implies that the actual DDR speed is twice that. But well, everyone kind of does it. I'm trying to avoid it, but everyone kind of does it. So anyway, for RAM, high clock speed, yeah, good, but low timings also good. So on Ryzen, safe bet is just test what your FCOK is capable of, then multiply that by 2, and that's the RAM speed you're gonna run, and then you just take your timings down at that frequency. On Intel, you can pretty much yeet the clocks as far as they will go, and then tighten down the timings. Now when it comes to what the timings do, not every timing has the same performance impact. In fact, the primary timings that you tend to see in XMP specs do pretty much nothing, like very little compared to what the sub-timings do. The sub-timings, meaning the secondary and tertiary timings, those are the ones where you can get big performance gains. And the one kind of issue I have with that is XMP doesn't actually set these most of the time. Sometimes your XMP does have sub-timings, but they usually tend to suck. So in pretty much 100% of the cases, unless you manually adjust your sub-timings are going to suck. And therefore your RAM performance is also going to be much, much lower than what it could be. Which is, by the way, also the reason why most YouTubers do these "Do RAM Speeds Matter" videos, and they just set XMP and see, oh, after 3600 there's basically no performance difference. Well, guess why? It's the sub-timings. Because all the way to 3600, your RAM clock tends to be the bottleneck, but after that, well, your sub-timings become the bottleneck. And if you don't change them, well, your performance is going to remain the same. Isn't that wonderful? But yeah, so that's the thing to remember. Your sub-timings give you big performance. Your primaries just look nice. Like, yeah, the TRCD timing, it is somewhat important. Like, the primaries still matter. But the sub-timings, which is what most people ignore, because, well, XMP doesn't set them, and they're never listed in the XMP speed. Why would they be important? Well, they are important. They are the most important. The primaries are not as important as the sub-timings. Some people actually recommend that you start out setting the sub-timings and then the rest. So yeah, they are very, very important. So keep that in mind. If you want fast RAM, set your sub-timings. So that's basically just, that's the first part done. Like, how does memory work and what gives you good performance? Now let's get into RAM ICs. Now there's a reason why I've put all these sticks down here. All of these are using, well, not all of them use different ICs, but they are a collection of different memory ICs. So as an example, these use Samsung 8 gigabit B die. These use Samsung 4 gigabit E die. This uses Micron 16 gigabit Rev B, and these use Hynix 8 gigabit CJR. So you can already see there's different naming versions, like Samsung RAM chips usually tend to be letter die, Micron tends to be Rev letter, and Hynix is really all over the place. For DDR4, it's just the last 3 letters of the name of the chip, so CJR in this case. On DDR5, they actually moved the revision letter one more to the left, so now you have to say 4 letters. So I saw people most people I just saw also apply letter die to Hynix chips now. So for DDR5, the naming might be a little bit different. But mostly for Hynix, it's just the last 3 letters, because like the first letter is the revision, and the rest is usually like FR or JR or whatever. Yeah. And why are these important? So your RAM IC is what determines how good your overclocking will be. Not your XMP, not your voltage, not whatever brand your RAM is from. The memory IC determines how good your overclocking will be. If you have the same RAM IC as someone else, you will probably be able to run the exact same settings. Not really the exact same settings, because there is a little bit of silicon lottery always involved, so each RAM stick is unique in some sort, so some might do one timing better than the other, or like there will be slight differences. But overall, if you have the same RAM IC as someone else, you will be able to run mostly the same settings as them. With one exception. We'll get to that later. So these two are a good example. Both of these, as I said, use Hynix 8 gigabit CJR. But one stick is rated for 3000, the other one's rated for 3600. Now, you would think, well, this is a faster stick, this must be better at overclocking than this. Well, as for the RAM chips themselves, the CJR chips on these are capable of the exact same clock. Now, there are some differences here, because this being a lower frequency means it's a cheaper kit, and Corsair actually used a very cheap PCB on this one that I was actually kind of surprised by. Basically, they're using a dual rank PCB for this stick, not a single rank one, which causes interference and makes overclocking worse. But that tends, like, I've never heard about this before, and you should not be expecting to get like a kneecapped PCB if you buy a like lower speed bin. You might get some extra capacitors on a higher speed kit, like you can see this faster kit has more capacitors on it than the slower one. But you're not gonna get like a handicapped PCB like this one usually. But yeah, like if you oversee the mess up that Corsair has made with the PCB of this one, both of these will overclock the same frequency, the same primary timings, mostly the same secondaries, the same kind of voltage. They will be generally overclock the same. And pretty much this goes for pretty much every memory IC. Not everyone though. So there are some memory ICs that are very inconsistent. As an example here, Samsung 8GB BDI, which is also the best memory IC, which tends to make things a little bit complicated. So Samsung 8GB BDI for DDR4 is just the fastest. It is just the fastest. It does best frequencies, best timings, best voltage scaling. It tends to be kind of heavy on the memory controller, which makes overclocking it sometimes a little bit harder. But overall, it's the best chip. And then this right here uses the exact same chip. So you would expect that this is rated for 4400. I've had it as high as 4600, and that's actually where the motherboard limited out. This chip, like the kit's capable of a lot more than 4600. You would expect that this right here is also doing the same. Well, no. This does 3600 at worse timings than this has at 4400. And the reason for that is the inconsistency of BDI. Now there's some other chips that also do this, but of the popular ones, BDI is by far the worst chip when it comes to inconsistency, because that's just it. It is very inconsistent. There is a much wider range of where the chips can fall to within Silicon Lottery. Like as I've said before, there are some slight differences between sticks, but usually generally it's the same. For BDI, the variance is so big that it's not even generally the same. The only thing they're gonna do the same is that they will work. Probably. So, yeah, when it comes to BDI, you very much want to get like at least like a good XMP. And by good, I mean 3200, 14, 14, 14 or better. If you get BDI with a worse rating than that, you can end up with stuff like this that has little to no voltage scaling, does low frequencies only with loose timings only. So BDI, you very much have to section off into binned BDI and unbinned BDI, because this is rated for 4400, so it will do at least 4400. This doesn't have any XMP on it. This one came directly from Samsung's factory and is only rated for JDEC at 2400. And there's just no guarantee it's going to do more than that, because there's no XMP on these. Like, treat XMP basically as a guarantee for you'll get at least this. But as you can see, you can get more depending on the memory IC, but for BDI, treat the XMP as you're going to get at least that as a guarantee. But of course it doesn't go for anything. So for example, this 4GB eDI stick right here is pretty good. It's very comparable to what a branded like Corsair eDI stick would do, because eDI is not as inconsistent as BDI. So that's just kind of thing to know. BDI is very inconsistent. There's other chips that do this too, but of the popular ones, BDI is by far the biggest liability for inconsistency. Like eDI is fairly consistent, CJR is fairly consistent, DJR, for example, is also consistent. 16GB Rev B from Micron should also be rather consistent. Yeah. So there are consistency concerns with some ICs, but most ICs will generally fall within the same range at the same settings. Now when it comes to voltage scaling, there's also a few outliers. So most chips will either tolerate or scale with more voltage. So like this kit's rated for 1.45 volts. I run this at 1.55 daily. This one's rated for 1.35. I run this at 1.45. This one also 1.45. The E-die also 1.5, 1.55 volts. Like most memory chips tend to tolerate 1.5 volts. They will either get faster or just nothing will change. So if nothing changes, you might as well pump the voltage back down. But usually, like chips will scale a little bit with more voltage to at least like 1.5 slots are like safe, because if you go higher than that, you might get into degradation territory on some chips. Except there are some few outliers. For example, CJR, you shouldn't go higher than 1.45 because it has been observed to degrade at over 1.45 volts. Like it gets steadily worse until it at some day doesn't work anymore. There's also Samsung 8GB C-die, which is very popular in 3216/1818 and 3600/1822/22 bins. That stuff is even worse because I've had a kit of C-die and other people had kits of C-die straight up die at 1.35 volts, which is the XMP voltage. They are rated for that voltage and yet they died at that voltage in like a month. Samsung 8GB C-die is an incredibly bad memory IC, which is why it only ends up in the very cheap XMPs and cause a lot of very disappointed overclocking beginners because they didn't know how to get a good IC. I was one of them. I had a C-die kit. Mine died, so I replaced it with this, which was much better and cost the same. So yeah, like if you want cheap RAM, like if you don't want to put much effort into getting good RAM, just buy Crucial, because Crucial only pretty much only sells Micron chips, and like you're gonna end up with like 8GB Rev E or 16GB Rev B, which are both pretty good. If you get like a cheap Corsair or G-Skill, you're probably gonna end up with C-die, and C-die absolutely sucks. So yeah, that's like the thing about memory ICs. They dictate how well you will overclock to. It's not tied, like, yeah, better XMPs will have better chips in them, but just because you have a good chip in a low XMP doesn't mean that the chip is trash, unless it's B-die. B-die low XMP sucks, and that's basically it. And yeah, like if you buy Crucial, because Crucial is owned by Micron, you will pretty much always end up with Micron chips. And those tend to be either 8GB Rev E or 16GB Rev B. Like if you get an 8GB DIMM, it's Rev E. So if you get a 16GB DIMM, it's usually Rev B. Those are pretty good chips. Like they both do pretty high frequency. Rev B does pretty good timings too. Good voltage scaling on both. Like if you want to put no research and still get good RAM, just buy Crucial basically. And yeah, otherwise, like if you want, let's pay attention to the IC, which puts us into the third topic. How do we find out what IC is in the memory kit? Because it's not like the manufacturers are telling you. The manufacturers are happy to tell you the XMP spec, which we've already established doesn't really mean much, because you can get chips that do, like literally, if you get the Crucial 3000 CL15 kits, they can probably do 5000. Like, just add 2 GHz to that. It will work. If it's Rev E, it will do that. So the frequency of XMP doesn't always mean much. The timings don't really mean anything because they don't really contribute to performance as much as compared to the subtimings. So pretty much all the info that manufacturers give you are useless for RAM overclocking. But not always. So the first thing for finding out ICs is most people will probably be wondering, how do I get B-die? Because it's just the best. B-die is the best. There's no question about that. How do I end up with B-die? Well, one solution is just buy the best memory kits, because only the best, like if you get the best memory kit, it will have the best chip, right? Pretty expensive. Also tends to not work really well because, for example, like B-die is the fastest chip, doesn't mean that it is the highest clocking chip. Well, it is the highest clocking chip, but it's kind of hard to clock it as high compared to like Rev E. Rev E will very easily do 5 GHz. B-die 5 GHz, kind of hard. but B-die will still be faster because of the better timings. So when it comes to B-die, if you want good B-die, look out for flat primaries. So it doesn't say it on the sticker here, but this kit is rated for 4400, 19, 19, 19. That's flat primaries, and also 1.45 volts. B-die likes voltage. So if you find a kit that's at 1.4 volts or higher and has flat primaries at like a pretty high frequency, very good chance that it is B-die. And this also goes for sort of lower frequencies like 3200, 14, 14, 14. That's B-die. Even if it's 1.35 volts, that's B-die because now the chip does low TRCD like that. Actually, the daily kit in my daily system is a 3200, 14, 14, 14. It's B-die. It's not very high voltage rated B-die, not very high clock rated B-die, but it's B-die. It does this pretty much does generally the same settings as this, which again confirms like same IC, same behavior, unless it's like low band B-die, that stuff doesn't count. So yeah, if you want B-die, look for flat primaries. Like 3200, 14, 14, 14 is a typical B-die bin. This 4400, 19, 19, 19 is a typical B-die bin. Sometimes you find things like 4000, 16, 16, 16, or like 3800, 16, 16, 16. 3600, 16, 16, 16 can be B-die. It can also be something else because 16 and 3600 is not all that tight. It could potentially be 8 gigabit DJR as well. So kind of pay attention there. But like, if you see flat primaries at over 4000, probably B-die. There isn't the 100% guarantee, but probably B-die. There's even a website that's like B-die Finder that like looks at specs and tells you, yep, that's probably B-die. So yeah, that's kind of how you find B-die. And there's actually other ways how you can find it out as well. So some manufacturers, that being Corsair, Patriot in the past, no longer, and G.Skill actually put what chip you have on the stick. They don't sell it, they don't tell it to you when you buy it, but once you have the stick, you can actually tell what it is. So right here you can see it says it's version 5.32. That tells you what chip it is. Because 5 stands for Hynix, 3 stands for 8 gigabit, and 2 stands for third revision or revision C, which is Hynix 8 gigabit CJR. So yeah, Corsair has the version number, which just straight up tells you what chip you have, which is very useful. It's just kind of sad that they don't tell it to you in the online shop. You can only tell once you have the stick in hand, because this version number isn't listed anywhere, and like you can get the same, like you can get, like I've actually had the exact same bin with 5.30, which is AFR, which sucks. Much, much worse than CJR. So it's not like, oh, because this is 5.32, every kit using this must be 5.32. No, that's not how it works. Then Patriot also used to have, like this is an older kit, it has this code. That's like 0 or O, I don't really know, BCFA. The C tells you it's CJR. Now you can see on my newer kit, which is B-die, they no longer include this. It's just not there. So it seems that Patriot has stopped doing this, which is kind of sad. And then there's also G.Skill. I don't have a G.Skill DIMM, but basically on a G.Skill DIMM there's a number called the 042 code. It's a long number that starts in 042, and it will end in 3 like letters, numbers. For example, 10B is Samsung 8 gigabit B-die. Like 10, as far as I know, means Samsung, and B means, well, B-die. Density, they don't list that. You can, well, if it's single rank in 8 gigabytes, then it's 8 gigabit. That's just, density can be calculated rather easily if you just know how many ranks you have and how big the DIMM is. But yeah, so that's how you can find out what chip you have, by just looking at the DIMM. Of course, you can also just look at the chips if you can somehow get the heat spread off without breaking it. There, the code will tell you what it is too. So 5WB, that tells you it's B-die. Now, of course, you can't always get the heat spread off, and sometimes the chips are actually rebranded. Like I took this apart, and these chips didn't say Hynix on them, they actually said Corsair on them, because Corsair put their own logo on the chips, which means you can no longer read the original part number, which tends to suck. So what do you do then if you can't take it apart or have rebranded chips and no sticker on the back that tells you which IC it is? Well, there is still one way, and that's called Typhoon Burner. So Typhoon Burner is a program that will read the SPD profile of your RAM. So the SPD profile is stored on this. This is called an SPD chip, and Typhoon Burner will read this profile. And on this chip, there is a register which is supposed to be set by the manufacturer what chip, like what IC you have. So if you get an OEM stick like this, it will be accurate because this identifies as 8 gigabits BDI. The problem is if you get a chip like a RAM stick from like Corsair or G-Skill or whatever, like other brand that's not directly the manufacturer of the actual chips, they tend to take the SPD programming a bit more loosely. You can get Corsair C-die sticks that have B-die programmed into them, which is very wrong. I wonder how many people shot 1.6 volts into their C-die and had it die instantly because of that. Probably more than 0. But yeah, so Typhoon Burner is only as good as the SPD profile programming is. And sometimes the program, like sometimes there is just also nothing in that register and the Typhoon Burner just kind of guesses what you have. So it's not 100% accurate. It's usually right, unless when you have a stick that's not specifically B-die spec and it says it's B-die, don't trust that. It loves to misidentify C-die as B-die. It happened to me. Yeah. So those are the ways how you can find out what IC you have. And other than that, it's really just the typical RAM overclocking procedure. It's just loosen out all the timings, set the frequency higher. Once you reach a wall, maybe test if higher VDIM works or if higher memory controller voltages work. If that works, keep going until you reach another frequency wall that you can't get over. Then once you're there, tighten down your timings one after another. And once you have all the timings as tight as they will go, there you go. You're done memory overclocking. Enjoy better performance. Like, if you set the subtimings correctly, even RAM ICs that don't do very well in overall overclocking will probably get a lot faster still, because just auto subtimings tend to suck, and XMP doesn't really set subtimings unless it does, in which case the subtimings will be trash anyway. Like, Buildzoid once made a video about how XMP actually makes performance worse, because he had an XMP that set the subtimings so loose that even the extra frequency and better primary timings were outweighed by these super bad subtimings, and he actually got a worse performance score. So, yeah. So we've sort of reached the end of the big sections I wanted to talk about now. Now just kind of remains a little bit more smaller stuff to talk about. So the first thing I wanted to talk about is PCB revisions, because there's different DDR4 PCBs. Now this is specific to DDR4. Of course, there's also different PCB revisions for other things, but I don't know the names of those revisions. So for DDR4, most sticks these days will use this layout, which is called the A2 layout. It's a single rank layout. So single rank means only one side of the DIMM is filled in. Dual rank would be this, which has both sides filled in. And this single rank layout is called A2. This is the most modern layout that most motherboards are optimized for these days, and most sticks will use these days. Then there is this, which is called A0. Now you can see the chips are a little bit more spaced out, and there's this empty spot for a 9th chip. Back is still empty. And this is kind of similar to A2, but slightly worse, because this empty bit causes some interference, and the chips are a bit more farther apart, which leads to some slight differences in how fast signals arrive at the chips and all of that. And then there's also the A0 layout, which I don't have a stick with, but on the A0 layout, all the chips are spaced out evenly, so you can see how there's like 2 groups of 4 on these. On the A0 layout, you have one big group of 8. And those chips are on really, really early DDR4, like stuff that came out when like X99 was a thing, or early Z170. And those tend to have a problem, which is a frequency wall at around 4600. You can't really clock it higher than that, no matter how hard you try. That's just a problem of how the traces are routed in the PCB of the A0 DIMM. That's just something that's really hard to get around. Now, thankfully, most new DIMMs don't really use that. It's like only when you like buy old DDR4 on eBay, you should check if the PCB you have might not cause some problems, because motherboards are optimized for A2, and other PCB revisions might have some difficulties clocking high or getting the same timings as an A2 because your motherboard might be optimized for A2 only. Some older motherboards, like for example my Z170 OC Formula, yeah, it has some problems with newer chips, specifically 8 gigabit chips too. It will probably also do a little bit better with A0. I don't have a stick to test, but it probably will do better with A0. So there's that. If you have an old motherboard, maybe look for A0 if you have problems with A2 sticks. And if you have a new motherboard, probably avoid A0. That's just kind of what to do. And then, of course, let's talk a little bit about more ranks. So this is a dual rank stick. You can see this on the sticker as well. It says 2R by 8. That means 2 ranks. This one, just 1R by 8. So 1 rank. These both use Samsung 4 gigabit eDie, and the 4 gigabit means that each chip holds 512 megabytes. So of course that means if you have only 1 rank, you can only make 4 gigabytes per stick, which isn't all that much. These days you want at least 16 gigabytes. So you can get a dual rank stick, which holds 8 gigabytes with 4 gigabit chips. And this actually has a unique advantage over single rank 8 gigabit chips, because of a thing called rank interleaving. Now I can't really go into exactly how it works, but basically there are some timings that are specifically for doing operations in the same chip or same part of the chip that you're in right now, and a different part or a different chip altogether. And doing the operation in a different part of the DIMM is faster than doing it in the same part that you're doing something in right now. And if you have more chips available to you, the chance that you do something in the same section of the DIMM that you're in right now is just lower than on a chip that only has 8, or even only has 4 chips. This is using X16, which means that these are 16 gigabit chips, but only an 8 gigabyte stick because, well, there's only 4 chips. These have a really big problem because of the same thing. There's only 4 chips. So 25% of operations occur in the same chip that's active right now, which make 16X chips really slow. Avoid these. This is not just on laptop memory. You can get normal DIMMs also in X16. There's also X4, but that only really exists on servers. Most DIMMs are X8, which means 8 chips per rank, which means single rank will be 8 chips, dual rank will be 16 chips total. Avoid X16 chips. Really bad for performance. Avoid, just avoid. So yeah, so that's chip arrangements and PCBs and ranks. I think that's pretty much it now. I think I've said everything I wanted to say. So yeah, I hope this helped someone understand a little bit more about RAM overclocking. Like, there is no be-all end-all solution. Like, you're gonna have to test around, but at least I hope this gave you a little bit of a better understanding of how it all works, how you get good performance, because it's not as easy as buying fast XMP. It very much isn't. There's actually, there is a lot of high frequency XMPs that have awful timings because, they're compared to B-die. A B-die with good B-die settings will be faster than Rev E settings at higher frequencies, because Rev E, everything has higher timings than B-die. B-die just does the best timings. That's why it's the best chip. So yeah, don't go by frequency, don't go by price, just go by IC, and keep in mind not all chips are always consistent, but mostly ICs are consistent. So for like Hynix chips, as far as I know, are pretty CJR, DJR, pretty consistent as far as I know. 16 gigabit Rev B from Micron, pretty consistent. 4 gigabit Rev E from Samsung, pretty consistent. 8 gigabit Rev B, not very consistent. So keep in mind for these. For these, you want to have at least a good XMP. For everything else, getting a 3000 CO17 or 3000 CO15 micron Rev E will do the exact same as a 3600 CO16 Rev E, because it's Rev E. It will do 5000 regardless. So, yeah. Video is long enough now, so thank you all for watching. Hope you learned something, and goodbye, for real this time.